So let me start by thanking the organizers for the opportunity to speak to you. I have to say I'm very sad I'm not with you in person. My university's travel rules are very strict, so I'm not able to come, but I hope I will be able to make up for it in the future to visit Prague and you guys. So I want to spend the next half an hour or so telling you some work I have done with actually a large number of collaborators. They are listed here on wave dark matter in general. A specific candidate would be some sort of axion, a light axion. In particular, I would focus on vortices, but more generally wave interference effects. And the majority of the talk is based on this paper on vortices. There's also a review that I've recently written, is on the archive on wave dark matter if you're interested in more background. So let me start from the beginning, where we all know dark matter is there. There's a lot of astronomical evidence for it. I'm not going to bore you with details of them. Suffice to say, they all come from its gravitational effects, of course, in many different aspects. What is amazing is despite the very rich astronomical evidence, we actually know very little about the basic properties of dark matter, as we all know. For example, if it is some sort of particle, what is the particle mass? I put here this vast spectrum that illustrates our degree of ignorance, right? We have no idea what the dark matter particle mass, if we were a particle, what would that mass be? It could be anywhere from what I would call ultralight, in this talk, 10 to the minus 22 electron volts, all the way to astronomical solar mass or tens of solar mass. These have basically the whole spectrum have been discussed in the literature, and we don't know. There is one actually scale on this spectrum that is actually interesting, and it's based on asking the following question. The question is the following. Let's start with the following observation, right? From astronomical measurements by looking at basically motion of stars, we know the total mass density in dark matter in the solar neighborhood, for example, and it's around this number, 0.3 GeV per centimeter cube. Based on that number, we can ask the following question. At what particle mass in this spectrum would the broadly wavelength be larger than the interparticle separation? So here's the question. The broadly wavelength, just to remind ourselves, is of course the inverse momentum, setting h bar to 1. And so it depends not only on the mass, it depends on the velocity. For velocity, we can just choose the known velocity dispersion of particles in the Milky Way, which is around 200 kilometers per second. Given that input and this number, the mass density, is very easy to check that if the mass of the particle is very light, then you need lots of them to make up this mass density. The interparticle separation would be very small. And at some point, it would be so small, it would be less than the broadly wavelength. And that's basically the question we are asking. And you can check, do the math. It turns out to be around this scale, that if the mass of the constituent or the particle is less than about 30 electron volts, you would be in what I would call the wave regime. The wave regime, basically, if I present it in a cartoon, it looks something like this. If I draw a sphere whose radius is the broadly wavelength, when you are in the wave regime, it means basically you are in a regime where you have multiple particles in the broadly volume. Another way to say is the interparticle separation is less than the broadly wavelength, right? Just by saying it that way, this particle has to be bosonic for that to even happen, because exclusion principle would forbid that from happening. So in this talk, we will be focusing on bosonic particle. In particular, for the most part, I will be focusing on the spin 0 particle, although a lot of the phenomenology could apply to spin 1 or even spin 2 if you want. Just to give you a sense of scale, if you set the velocity to be 200 kilometers per second, appropriate for the Milky Way, as you dial the mass up and down, less than 30 electron volts, the broadly wavelength is basically of this scale. If, for example, as you might know, some of the QCD Axion detection experiments, their target mass is just around here, 10 to the minus 6 electron volts. That's why I picked this scale for illustration. The broadly wavelength is not astronomical, but it's still pretty large. You can see it's about 1/10 of a kilometer. And it's certainly large compared to the size of the detectors, which means actually, as we will see towards the end, the wave effects actually have implications for those Axion dark matter detection experiments. Of course, if you dial the mass all the way to ultralight, 10 to the minus 22, then the broadly wavelength would truly be astronomical. And as you can imagine, there are a lot of interesting astrophysical effects, which I'll talk about. Now, for the rest of this talk, sometimes I'll be focusing on ultralight for illustration, but most of the effects actually occur regardless of whether you are in the ultralight end of the spectrum or you are more like 10 to the minus 6 electron volts. As long as you are less than 30, most of what I'm going to say applies. This is what I mean by the wave regime. Okay, so here's an outline, right? So we are going to start with very briefly just some particle physics motivations. Why are we interested in such a light particle to begin with? That's going to be very brief. The bulk of the talk would be on the wave dynamics and the phenomenology. And it's a very rich subject. I'm just going to pick out one subtopic, which is the topic of vortices for illustration. And then I will end with some thoughts about astrophysical and experimental implications. Again, for astrophysical implications, most of them, not all of them though, most of them are relevant if you are in the ultralight end of the spectrum. Let's say 10 to the minus 20 or lower. Whereas for dark matter detection experiments, you don't need to be in that ultralight range. The wave effects could still be irrelevant. Okay, so let me start with the particle physics motivations. This I'm going to be extremely brief. If we are interested in a light scalar particle, spin zero particle, a fairly natural candidate is some sort of pseudo Nambu-Goldstone boson. If it's a strict Nambu-Goldstone boson, of course, it will be massless. Hence, we add the word pseudo here. It means basically there is some small breaking of the shift symmetry that gives the particle a mass. And there are a lot of examples like this in the literature. The most well-known one, and perhaps the most well-motivated one, is the Qcd Axon. And here I show you a picture that kind of illustrates the idea. The axion is basically the Goldstone associated with the angular field, basically. It's this angular field. And non-perturbative effects can generate a small potential, a small mass, basically tilting this mass can have potential ever so slightly to give the particle a small mass, right? And of course, there are also, as you might know, other possible axions, or more generally, they're called axion-like particles, not necessarily the Qcd axions. They arise in string theory, for example. Essentially, there are zero modes of higher form fields when you have compactified dimensions. And so here I'll just leave it at that, right? So there are a lot of candidates from that point of view for a light spin zero particle. I want to spend maybe a minute or two just talking about the ultralight version, right? So this is the ultralight version, and it's worth just telling this story a little bit. So by ultralight, we mean something like this, although as you will see just in a minute, there is actually a pretty wide range, even what I call ultralight. And the story is something like this. This angular degree of freedom, which I call phi here, it has the normal kinetic term, and it has a potential again, because this potential is generated by some non-perturbative effects, assuming the associated instanton action is moderately big, like 100 or 200, this energy scale lambda is going to be exponentially suppressed, very small. You do expect some kind of cosine structure because this is an angular field after all. And there is an energy scale associated with basically going around in circle. And that energy scale is, I call it F here, is often called the Axion decay constant. If you expand out this cosine, then you can read off the mass term from the quadratic term, and it goes like this, right? So to the extent lambda is exponentially suppressed, the mass would also be very small. The Axion decay constant, we do not know what it, how big it should be, it's basically a free parameter, but potentially it could be actually fairly high, gut scale or even close to Planck scale. There is a very simple story that suggests that the ultralight mass is interesting from a cosmology perspective. And it basically comes from this story about computing the dark matter abundance today from the a relic of the Big Bang. Basically, the name of that story is called Misalignment Mechanism. And the story is actually fairly simple. So imagine the scalar, this, from now on, I'm going to call it the Axion. Again, not necessarily the Qcd Axon. In fact, it's not going to be the Qcd Axon. This Axion, let's say, has some primordial value. This is the potential. This potential is now sketched out here in this cartoon version. The primordial value, let's say, is not exactly at 0, where the true minimum is, but is some value. And let's say that value is not particularly fine-tuned, meaning this angle, phi over f, is order 1. It would get stuck here because of Hubble friction until when the Hubble expansion rate becomes low enough to basically come down to the order of the mass scale, which is the curvature scale of this potential. Then the scalar can roll down the potential and commence oscillations. And in fact, as the universe expands, that oscillation amplitude will become smaller and smaller. It's taking energy out of the oscillation amplitude. And you can actually just reinterpret this as basically the usual redshifting of energy density in or particle number density when you have non-relativistic set of particles. And following this story, I'm skipping a number of steps. You can actually compute the relic abundance, and it's basically this formula here. So the omega in matter density or Axion density is of the order of what you need, around 0.1. Provided you make two assumptions. Number one is that the Axion decay constant is relatively large. Here is chosen to be 10 to the 17 GeV. It does seem to arise in a lot of scenarios involving string theory. And the other is you choose the mass of the particle to be ultralight, like 10 to the minus 22 electron volts. If you make these choices, you would actually in this very simple story have the correct relic abundance today to match basically what you need to account for dark matter. But I should say there are assumptions involved here, right? So let me spell out the assumption. One is I assume the misalignment angle, so to speak, phi over f is order 1. Number two, I assume the potential is just constant. It doesn't change as you evolve backward in time. For Qcd Axon already, that temperature, that potential is temperature dependent. So that this could be slightly modified in the Qcd Axon case, although in the end the numbers work out fairly similarly. And of course, crucially, if you look at the dark matter abundance, it actually depends more strongly on our assumptions about f than on m, right? It goes like f squared and m to the 1/2. And clearly, since this kind of fundamental physics scale is just unknown, if you dial it up and down, the necessary mass can have to change a lot to match the observed abundance. So keep that in mind, right? So This story, I would say, is merely illustrative that suggests that it might be interesting to consider a fairly light dark matter particle. At least there's a simple story that you can tell that give you the correct dark matter abundance. Okay, so it's merely a motivation, if you like. Okay, so let's now switch gear and talk about the dynamics now. So here we are interested in now a bunch of Axion particles, which is basically described by these oscillations around the minimum. And in fact, as the universe expands, you'll be oscillating closer and closer to the minimum. And therefore, for the most part, you can just ignore this whole cosine structure and focus on m squared phi square potential. And that's what we're going to do. And so the correct equation is the simple one, it's the familiar one, the Klein-Gordon equation for our Axion particle phi. For cosmology purpose, we are typically interested in the non-relativistic regime because, for example, think about the Milky Way. No, the velocity of particles in the Milky Way, they are not relativistic. It's 200 kilometers per second. So it is useful to follow a very standard strategy to take the non-relativistic limit, and the strategy is like this. So phi, the Axion field, is real. You can decompose it into a complex scalar psi and its complex conjugate like so. And you factor out the primary time dependence, which is the oscillation with frequency m, which is very natural if you just look at this equation and look at a homogeneous field, right? You would have that frequency m. So you factor that out. And the non-relativistic limit is basically saying, let's assume psi, whatever time dependent it has, is slow. It's slow compared to the time scale set by n, basically. Once you do that, you plug into the Klein-Gordon equation, you get the standard Schrödinger equation. The thing that I should explain a little bit is among interactions for the Axion particle, because from the very beginning, we are ignoring quartic, for example, that you would have if you expand out the cosine. The only interaction left is really gravitational, which is captured by basically the gravitational potential here. And the gravitational potential is basically sourced by the dark matter particles themselves. So it's just mass times the number density of particles, psi square, that sources the gravitational potential, and that becomes this potential term here in the Schrödinger equation. And so in terms of the dynamics, is an extremely simple system. All we have is just these two equations, the Schrödinger equation and the Poisson equation. If you want to make it a little bit more sophisticated, you can include the expansion of the universe, but it's a small change. Essentially, everything is captured by these two equations. I should also say, despite the appearance of a Schrödinger equation, which means we are talking about waves here, and I'm going to call this psi the wave function following common terminology. Despite its appearance, what we have here is really a classical system, meaning psi, the wave function, should be thought of as a classical complex scalar field. Perhaps an analogy here would be useful. Let's think about photons. If I have a state with many high occupancy, many photons, generically, very often it is true that you can describe what is going on with just classical electromagnetic waves or classical electromagnetic fields, satisfying the Maxwell equation. Here we are basically talking about a very similar kind of situation. Okay, so we are going to have wave phenomenon because this is a wave equation. But the wave phenomenon is basically classical wave phenomenon. Now, let me also mention an alternative point of view, which is thinking about this system as describing some sort of a fluid, which is helpful for qualitative understanding, is to think of this as representing a fluid in the following sense. I already told you, the density, the number density of the particle is psi square. And so it's very natural to think of psi, the complex scalar, as having an amplitude scale as square root of the density, the mass density rho. And because psi is a complex field, it must have a phase in addition to the amplitude. So I call it theta here. And you can convince yourself that the Schrödinger equation actually implies these two equations in the fluid variables. One is just conservation, mass conservation. And mass conservation is not a surprise, because if you look at the Schrödinger equation, as we all know in quantum mechanics, there is probability conservation, which just follow from the U1 symmetry. And the analog of that in this fluid description is mass conservation. Or put it in another way, in the non-relativistic regime, you do not create or destroy particles. So that's particle number conservation. That's basically what this expresses, with the particle velocity actually given by the gradient of the phase. You can see, you can see it here. Now the Schrödinger equation is complex, so it should have two independent real equations if you want. One of them is conservation. The other is Euler equation, written like here. It should look fairly familiar. The left-hand side just gives you the Lagrangian time derivative of velocity. It's basically fluid acceleration. It has two contributions. One is just gravitational, right? The gradient of the gravitational potential. The other one might look slightly unfamiliar. It's often called quantum pressure in the literature. And I'm going to use the same term, although it's a little bit misleading. It's not really pressure. But nonetheless, I'll use that term. And basically, this term encodes the wave effects in the following sense. Once you write in this fluid equation, it's fairly obvious what does it mean to talk about wave versus particles. If you send m to be very big, you can ignore the last term. And these two equations, without this very last term, just describe basically a pressureless fluid, right? With the only interaction being gravity. So that's usually what we use to describe, for example, just usual cold dark matter, like WIM, for example. On the other hand, if m is not super large, there would be scales at which you should keep this term. And in a sense, we are interested in precisely the regional parameter space where this term actually plays an important role, where you have wave effects. This sort of fluid, by the way, you could think of as some sort of superfluid if you want, in the sense that the velocity is pure rate gradient flow. That is going to be important in what I'm going to say in a minute or two. Okay, so this slide basically tells you everything you need to know the dynamics. Everything I'm going to say just follow from these equations, in particular, for example, the Schrödinger-Poisson equation. I'm going to pause here in case there are questions, although I guess probably mostly the questions happens at the end.
In the room, there is one question actually. Just one question about the amplitude that you go over the previous slide. The parameter f, the capital F, appears in the energy density just because you assume that that essentially the displacement is equivalent to F, right? So that's the only reason that parameter F. Otherwise, it only depends on the mass. I mean, right?
Sorry, you're talking about the radic abundance calculation.
Yeah, so the omega matter there, the only reason there is this capital F in the, it's only because you assume how far away it is from the minimum, right?
It's because of that, yes, it's because of that.
Yeah, okay, okay.
Thank you, thanks for asking.
Well, yes. There's one more.
But I'm just wondering, so if it expands this axiomatic potential, then the self-coupling constant, of course we don't know about this cosine structure, right? Just look at, let's say, phi to the 4 term, then the self-coupling constant would be like 10 minus 96, right? For this parameter. But probably there is no way just so small. There's no way to probe it any further, right? Therefore, in a sense, we would need to kind of live with the theory that we have lambda 5 to the 4, very small mass, and even smaller coupling, self-coupling constant. Like, what do people think about this?
Yeah, I couldn't hear you very well. I heard lambda 5 to the 4th. So for sure, if you expand on the cosine, there is a self-interaction of the axion. Is the question about how important that term is? Was that the question?
Well, it's extremely tiny self-coupling constant. It's basically for the values which are good pivot points for omega meta. That would be like 10 minus 96.
Yeah, it's very small. Yes.
Yeah, and formally speaking, we don't, of course, talk about even higher orders. So formally speaking, we would be okay to either massless theory, so masses with theory with tiny masses, and then this tiny self-interaction coupling constant. But people will not know that there is this cosine at all.
It will be hard to know. Yes, yes. That's good
So
point.
frankly speaking, it's okay to just talk from this lambda 5 to the 4, and with extremely tiny coupling constants, they are okay in that perspective.
Yes,
right?
I agree with you. I agree with you. From the point of view of what I'm going to say below, it doesn't really matter. This whole story about misalignment mechanism is just an additional motivation. It's just an additional motivation for thinking about this one. But you can decouple. You can decouple what I'm going to say below from basically this story for sure. By the way, it's good that you raised the question of self-interaction. So the lambda, indeed, as you said, if I choose this parameter, is extremely tiny. Lambda is basically m over f squared. Now, it is true though. You can actually imagine astrophysical situation where even that extremely tiny lambda is relevant, because the self-interaction actually scale with the density of the dark matter particle square. So if you happen to be in a situation where the dark matter density is actually very high, which could happen, for example, if you have for some reason, some very compact object, or you go back to the very early universe, it could happen that even that tiny self-interaction is actually relevant. But for the most part, I'm going to ignore it. Yeah.
Great.
Okay.
Thanks.
So yeah, you have about 15 minutes left.
Thank you. I think that should be sufficient. So let's see. So let me skip this slide. Let me also skip this slide just to say there's of course a lot of prior literature on scalar field dark matter. So what are the wave effects I'm talking about in the remaining 15 minutes? Let me just play this movie as I speak. No. So what is this movie? This movie is basically a cosmological simulation. You have small perturbations in the early universe, and you just evolve the Schrödinger-Poisson system forward in time. And over time, of course, you form things that are basically halos, like this one here and this one here, and there are filaments that connect them. And by the way, this movie that I just showed you is not a true movie in time. It's really just the cosmological box at some final time, low redshift, and I'm just showing you slices as we go along in, let's say, some particular direction, just to show you the 3D structure. But I hope it's clear when you look at this movie that there are actually interference fringes. You can see here along the filament and also surrounding and even inside halos. And it is an inevitable consequence of having waves, basically. One way to think about it is the following. If you have a halo composed of a set of waves sloshing around with different momenta, for example, these waves in general would have random phases. And that you would have places where just by accident you have constructive interference and places where you have destructive interference. It's just unavoidable. And therefore you are going to find interference fringes. The typical size scale of these fringes is basically the de Broglie wavelength. If you give me the velocity dispersion of the halo, you compute the de Broglie wavelength, you would figure out the typical size scale of this interference substructure. And that's what we are going to focus on now, right? Okay, so there are many implications of having dark matter basically as waves. We cannot possibly talk about all of them. I'm going to focus on vortices. I think I'll close with some thoughts on what they mean for experimental direct detection and also astrophysical observations. I doubt I will have time to talk about actually combining vortices with black hole, which is actually very interesting. Maybe I'll mention that at the end. So let's talk about vortices. So the first question you might have is why we even want to talk about vortices, because I actually told you in the fluid interpretation, velocity is pure gradient flow, right? Gradient of the phase of the wave function. So the vorticity, which is the curl of this, is just strictly zero. So how can there be vortices? There is one loophole in this argument, in this fluid formulation, if you want, which at first seems like a very tiny loophole, but it turns out to be very important. And it's the following. Suppose you happen to be in a place where you have complete destructive interference. When I say complete, I mean, let's just pick a point where the destructive interference is so complete that the wave function is actually zero. And if it's zero, the amplitude is zero, of course. At that point, the phase is actually ill-defined. You cannot even talk about the phase at that particular point. And this turns out to be, this tiny loophole turns out to be sufficient for you to actually think about vortices. In fact, what I want to convince you is that the location where this happens is precisely the location of a vortex. Before we get there though, let me kind of make 2 points, right? One, in order to have complete destructive interference at all, it's actually fairly important you have at least order 1 fluctuations. Think about it this way. In the early universe, the wave function is more or less homogeneous with 10 to the -5 fluctuations, say. And therefore, even if you have destructive interference, it can never bring the wave function all the way down to 0 because you just have 10 to the -5 fluctuations. So to have complete destructive interference, you have to wait until the fluctuations becomes large enough, basically go nonlinear. And then you could have this complete destructive interference, which means what I'm going to tell you about vortices, it can only happen because thanks to gravity, basically. Gravity amplifies those fluctuations. That's my point number 1. Point number 2 is a question that I will address later. Since I'm making use of this apparently tiny loophole that this complete destructive interference can happen, and therefore rho can be 0, the amplitude can be 0, you might reasonably ask, how often does that happen? It turns out it actually happens very often. So postpone that question, I'll come back to that, right? And also let me say, this whole subject of vortices is very familiar in the condensed matter literature. People talk about vortices in superfluid, for example. The only novel aspect I have to in what we say is that in our case, this happens because of gravity. That's the only novel aspect. Otherwise, most what I'm going to tell you is known and well understood in the condensed matter literature. So let me start, right? So the first point I want to make is the following. Let's ask ourselves, if I have a set of points in 3 spatial dimensions where both the real and the imaginary part of the wave function vanish, what would those set of points look like? Well, it's actually fairly simple. In 3-dimensional space, you ask what are the set of points where the real part vanishes. Generically, it would be some kind of surface. And likewise for the imaginary part. And generically, those 2 surfaces are going to cross and form a line. And so just based on this very simple argument, you do expect a set of points where both the real and imaginary part of the wave function vanishes would be some kind of a line. So from our point of view, it will be some kind of line or string defect. And furthermore, now let's go to the second point. Let me draw that line here, right? This purple line is basically a line at which the wave function, both real and imaginary part vanishes. And remember, along this line, the phase is ill-defined, but away from the line, the phase is completely well-defined. And for the wave function to be a single value, the phase must wrap around by integers of 2 pi. And if you recall, the gradient of the phase is the velocity. It basically tells you the circulation, the velocity integrated along a loop. Basically, this loop that I draw here must have actually these quantized values. Okay, and basically just based on that, you can basically conclude. Okay, look, you have a vortex. The location of the vortex is precisely the line along which the wave function vanishes. You can actually say a lot more. For example, let's do a Taylor expansion argument. No, suppose I pick a point on this line. Let me call it the origin. The wave function vanishes there. Let's do a Taylor expansion. This is the first order term. Assuming the first order term does not vanish, what does this tell you? Well, if I square this to get the density rho, it tells you basically, as I move away from this line, the vortex, the density must rise as R squared, close to the vortex. It's a generic prediction. And furthermore, the velocity profile is also very well predicted because, again, this circle, this loop circulation is basically a constant independent of how big the loop is. And therefore, the velocity must scale like 1 over R, as R meaning the separation from the vortex. And furthermore, it's not hard to convince yourself these vortex lines, kind of like magnetic fields, they cannot just end. So they form a loop. So what you have is actually a vortex ring. And so these are all fairly simple kind of deductions you can make without doing too much work. I should say, just a parenthetical remark, since we are talking about defects, the kind of defect that I'm talking about is not the same as the Axion string that you might be familiar with. The Axion string is a topological defect associated with the Petri-Queen U1, if you want. This is a defect associated with a U1 that has nothing to do with the Petri-Queen U1. It's just a U1 associated with particle number conservation in the non-relativistic limit. Okay. After all these arguments, let's show you just some simulations now. So knowing that these things might be there, it will be good to take one of these cosmological simulation. You find a halo and you identify the vortices. And this is one particularly nice halo, strictly symmetric halo. I'm not showing you the halo. I'm just showing you where the vortex rings are. You can find them. To find the vortex rings is important to check the phase. Basically, the robust thing to do is to check that the phase actually wraps around, which we can do in a simulation. If you have a more realistic halo, the vortex rings would be more messy, basically like this. You can check that the density profile close to the vortex ring does Rayleigh distance square, which is what the Taylor expansion tells you. You can check the velocity profile drops like 1 over R. So these things all checks out. And in fact, a vortex ring in general is very interesting. Not only does it have circulation like this, you can also show the vortex ring must have bulk motion. And in fact, the bulk motion is inversely proportional to the size of the vortex ring. Now, these vortex structures are very dynamic. They do not sit still. They do not, they can nucleate from 0 size and expand. They can join together. They can also shrink to 0 size and disappear. So all these things can happen. It's very dynamical. So let me just make a few simple points. Number one, which is the question that I raised kind of earlier. Should these defects be rare? Remember, in my way of motivation, I'm motivating this by saying, okay, occasionally you are going to have complete destructive interference that bring the wave function to 0. One might reasonably suspect or ask that, shouldn't that be very rare? It turns out actually it's not rare at all. Generically, you can show both analytically and just by checking the simulations that you have one vertex ring per de Broglie body. Essentially, the de Broglie scale is the only scale in the problem, and this is the generic prediction: one defect or one vortex ring per de Broglie body. Number 2, I already said earlier, motion, bulk motion of the rings. Number 3, I also mentioned, the vortices, they are transient phenomena, they change. However, the time scale can be very long for the change. The time scale can again be estimated using the Broglie wavelength. You just take the Broglie wavelength divide by another power velocity. And if you choose ultralight, for example, dark matter particle mass, that the Broglie time can be very long, millions of years, enough for it to actually imprint itself in astrophysical observations. Okay, and let me skip this point. Okay, and with this kind of understanding, you can actually predict actually what kind of fluctuation you should see inside a halo. Here I plot the probability of density inside a halo, and you can actually match what you measure from simulation very well using just some kind of random phase approximation. Let me skip the detail here. I think how much time do I have remaining, or am I running out of time already?
Minutes.
Sorry?
You have about 2 minutes.
2 minutes, okay, fantastic. So I'll spend 1 minute on astrophysical implication and 1 minute on experiment, okay. So observational signatures, this applies when you have ultralight dark matter. If you have indeed this interference pattern, basically they form some kind of substructure in your halo that is inevitable because of wave dynamics. What it does is it would change, for example, observation of gravitational lensing. So here I show you some images of strong gravitational lenses where you see multiple images from the same quasar lensed by a foreground galaxy. You can actually show that if you have 2 images that are very close together, if the lensing halo is very smooth, it doesn't have substructure like this wave interference substructure, then 2 images that are very close must have the same magnification actually. In the limit, they get closer and closer together. Whereas if there's substructure on scales smaller than or equal to the image separation, it would cause differential magnification between the 2. And this is something that you could look for. This is something people call flux anomaly. And you could do simple estimates, which we are trying to refine now, that these flux anomaly is at least at the 10% level, could be bigger, is observable. The other observational implications, again, in the ultralight regime is you can also look for the impact of this interference substructure as it scatters stars, basically. This is a nice image of a globular cluster, the tidal tail, when it's tidally disrupted by our own galaxy, the Milky Way. And this nice and cold tidal stream, as it orbits around the galactic halo, is going to encounter these interference substructures and get heated up, basically. And essentially, you can look for dispersion of the star over time and to check for what kind of substructure you have. That's another possible thing one can do. Let me end with some thoughts about experimental detection, which is also very interesting. So here, we are not necessarily interested in ultralight axion. It could be just light, 10 to the -6, for example. The axion detection experiments, there's a wide variety, of course. Typically, you're trying to use the axion coupling to photons, like so, or axion coupling to fermions, like so here, where this little f basically is the same as the axion decay constant I talked about earlier. The main message I want to get across is very simple. Traditionally, people often have in mind an axion detection experiment. If I have a detector, what I'm trying to find is an axion field that oscillates in time like this, right? Where the frequency is just set by m, the mass of the axion. So that's traditionally what one think of as what the kind of the target signal of an axion detection experiment. What I'm trying to tell you is the following: because of these waves with random phases with their interference substructure, is inevitable that actually the Axion signal at a given location would actually look more like this. It would have this fast oscillation with frequency m. So if m is 10 to the minus 6 electron volt, the time scale is very short, 10 to the minus 9 seconds. But it was going to have this slower modulation precisely because of this more or less stochastic interference pattern. And that is on a longer time scale, it's basically the de Broglie time, 10 to the minus 3 seconds. And these experiments are sensitive to time scale actually shorter than this, meaning they are going to be sensitive to this kind of stochastic wave phenomenon. And I just want to leave you with three kind of thoughts associated with that, right? Number one, because of the stochastic nature of your signal now, it has this long time scale modulation because of wave interference. It's actually best to think of Axion detection experiment as a measurement of correlation functions, kind of like what you would do in the CMB if you want, or in radio astronomy. Number two, if you happen to have a vortex that passes through experiment, what you will see depends on which experiment. If you have experiment that is sensitive to phi or is time derivative, when a vortex passes through, your signal will go to 0. But if you have an experiment that's sensitive to spatial gradient, like this coupling to fermion, your signal will not go to 0. So vortices actually has different implications for different experiments. Number three, perhaps the most, in my mind, the most kind of fun thing to think about is the existence of vortices is basically telling you the Axion field, if you expand it out as an amplitude and an oscillation phase, this phase data here has interesting space-time structure, and it's fun to think about what experiments can do to actually capitalize on that structure. And I think I'm running out of time, so I'm going to just skip this topic of vortices combined with black holes. And I'll just end with this summary. I hope at least I get across the point that if you have dark matter particle that's light enough, less than about 30 electron volts, you have interesting wave phenomena. Thank you for your attention.
Thank you very much. Okay, so people on Zoom, please raise your hands, but I will start with Diego Blas.
Hello, can you hear me?
Hey, Diego.
Hi, how are you? Yeah, I wanted to ask you if you can connect the fourth point with the fifth point of your list, in the sense that, at least in these superfluids, I know that the friction can be higher because as you move in a medium, you generate vortices and they generate anomalous friction. So in the ultralight dark matter, dynamical friction is reduced, but I wonder if you, by the creation of vortices, I mean, I don't think this has been studied. I thought about it, but I wanted to ask this to you a long time ago. So
yeah, that's a great point, Diego. I think you're right. So our original calculation regarding dynamical friction assumed the medium is basically homogeneous to start with. It doesn't have all these interesting interference substructure like vortices. If they were present, I think the dynamical friction would be reduced less. It would not be reduced by as much. The question is how big. It's worth a calculation, Diego. I think it's a great question.
Maybe Sabir Ramazanov.
Thanks for the talk. So I have a question. I heard that from some papers that so for you it's crucial that vortices form for vortex formation that the wave function is turned into 0. And at the same time, I heard that the side turning into 0 is crucial for multi-scheme formation of the halo. And so can we somehow affect the dark matter halo formation in this picture? Because multi-stream will be accompanied by vortex formation as well.
Yeah, I heard the part of the question about the fact that we are for vortices, we are of course interested in psi equals 0. I could not hear the rest of the question, unfortunately.
And psi equals to 0 is also crucial for multi-stream formation at the onset of halo formation. It's psi equals to 0 is associated with shell crossing multi-stream. So and if multi-stream is accompanied by formation of vortices, maybe it could impact somehow on halo formation in the end of the day.
Yeah, that's a great point. So here I'm mostly focusing on vortices in a halo that's already varialized, so to speak. But for sure, when you have a very dynamical situation where you have a collapse of a halo and so on, or like what Diego said, you have something that's moving through your dark matter fluid, that whole process could generate vortices all on its own, like what you're saying, like associated multiple streaming and so on. And I think we need to do more work to study, actually, in some sense, the generation of vortices itself. Yeah, away from this very simple, almost like kind of thermodynamic limit where you just have a varialized halo. I agree with you. It's a very interesting question to study.
And then we have a question on Zoom from Sergei Sibirakov.
So hi again. So yeah, that's very interesting idea about this flux anomaly. So can you say a bit more? For example, how do you plan to distinguish it from foregrounds like lensing by micro lensing by stars and this kind of things?
Nice, nice. So there are a few things that could be confused with it. First of all, there could be substructure just due to subhalos, right? So it doesn't even have to be this wave interference phenomenon. It could be just subhalos. So even CDM, regular WIM CDM would have subhalos. The way to tell it apart, tell those two things apart, and also actually similar for microlensing, is to measure the following. So in the future, I think we are going to have flux anomaly measurement as a function of angular separation. And essentially, once we have that kind of measurement, we are basically probing the substructure power spectrum, if you want, as a function of scale. And these different kind of possible contaminations, so to speak, they would all be associated with different power spectrum shape, basically. And the wave interference effect give you a very special power spectrum that basically, in some sense, it peak at the Broglie scale. Mm-hmm. Now, whether future measurements are, the data are good enough to distinguish all this possibility, I don't know. It remains to be seen. But at least conceptually, in principle, you can tell them apart. Whether the data are good enough to do that, yeah, that's harder to say. Requires more work. For microlensing, by the way, Sergei, microlensing usually mostly is you can tell all them apart by also comparing radio observations versus optical observations.
Okay. Why is that? Yeah, why radio optical will be different?
Yeah, because microlensing relies on the source being small compared to the Einstein radius. Yeah. And usually the source size depends on wavelength, depending on whether you are optical or radio. Radio tends to be very big, right? Radio source, you have jets and so on. The radio source tends to be very big. And so microlensing is less important.
I see.
Yeah.
Okay, so let's thank Lam again because we're running out of time.
Thank you.